Hi everyone, Dr. P here, and in this video we're going to go over the answer key, for the Chapter 1 class activity. Alright, so let's start with number 1. From 1973 to 1995, the United States had a national speed limit of 55 miles per hour. What is this speed limit in meters per second? Alright, so we can set up this conversion. We will say meters per second equals, we'll start with 55 miles per hour, and then we'll multiply that. A convenient factor to do is kilometers per mile, and again, as you may have noticed, on the back here we have 1 mile equals 1.61 kilometers. So 1.61 km. That number is not exact. And then so our miles will cancel. And then we need to get to meters, so let's have meters per kilometer, or kilometer, and that's 1,000 meters per kilometer. So our kilometers cancel, and we have meters. Now to get seconds, we need to convert our hours to seconds. And the first thing we can do is convert to minutes, 1 hour per 60 minutes. And next we'll convert from minutes to seconds. And there's 60 seconds, sorry about that. 60 seconds per minute, or 1 minute per 60 seconds. Now I can go ahead and with my trusty calculator here, I can start multiplying these. 55 times 1.61 times 1,000 divided by 60 equals 24.5999. So this should be 25 meters per second if 55 mph is not exact. It would have more sig figs if it was exact. We would get a third sig fig, so 24.6 meters per second. Okay. All right. Next question. The engine in Dr. Pitcher's car has a displacement, or volume, of 1.5 liters. What is this volume in cubic inches? Inches cubed. All right, so I want to set this up as inches cubed equals, and I start with 1.5 liters. Now let's take a look at units here. I know from liters I can get milliliters, and then from milliliters I can get cubic centimeters. And if I have centimeters cubed, I can convert that to inches cubed because I have an inch to centimeter conversion there. Alright, so let's first convert our liters to 1,000 milliliters, liter per 1,000 milliliters. And now 1 milliliter per 1 cubic centimeter. And now every inch has 2.54 centimeters. But I have to cube that. So centimeters will cancel there. So now that gives me 1.5 times 1,000 divided by 2.54, and let me cube that. Whoops, that's not the right thing here. Let me clear that out. 1.5, there we go, I can see that a little better, times 1,000 divided by 2.54 cubed. That should give me 91.5. So because the 1.5 is not exact, the answer is 92 inches cubed. There we go. Okay. Next question. The density of gold is 19.30 grams per milliliter. Dr. Pitcher's wedding band, yay, has a mass of 5.7 grams. Calculate its volume in milliliters. And then what assumption do you have to make to do this calculation? All right, so if we have milliliters, we want to get milliliters, and we're starting with grams, we will divide by the density, or multiply by 1 over the density. So density is 19.30 grams per milliliter. So we would write our conversion factor as 1 milliliter. I can put a 1 here. 1 milliliter per 19.30 grams. In fact, maybe I'll go ahead up here and put 1s in front of some of these here, just so per 1 mile, kilometer, just so 1 liter, just so we keep everything straight there. Usually if you don't see a number, you assume it's 1. All right, and then that will give me 5.7 divided by 19.30, and I will get 0.29, etc., but it is limited to 2 sig figs by the 5.7, so that would be 0.30. Now, the assumption we're making is that my wedding band is pure gold. And it's not an alloy with other metals. Now it turns out that, I think as I mentioned in one of the lecture videos, that my wedding band is 14 karat gold, which is not pure gold. Carats refer to 20/4 of gold, so 14 carats would be 14 20/4, which is 58% gold. So the density of this ring is probably more like around, I don't know, 12 or 14, maybe like 12 grams per milliliter. If it was 24 karat gold, that would be 100% gold, and then this assumption would be a valid assumption. All right. Now for problems on the back. For each of the following calculations, indicate how many significant figures the answer should have. You do not need to do the calculations. All right, first one here, we have 1, 2, 3, 4 sig figs, and 1, 2, 3, 4, 5. It's a multiplication, so the answer should have 4 sig figs, because 4 is the fewer sig figs. B is a little tricky. It's asking for sig figs, yet it's an addition. So if I set up this addition, I would have my answer here, and I'd cut it off right there, or I do my rounding, because I have 1 decimal place on the 5.3. So my answer would have 1, 2, 3, 4 sig figs. So that's 4. Now here again, our assumption, as I mentioned, we're assuming that 32, 9, and 5 are all exact because this is a temperature-like calculation. So our limit is going to be the 3 sig figs there. Okay, because 32 is exact, it has infinite decimal places, so we're limited to the 1 decimal place, and then we'll end up with a number that has 3 sig figs. Those aren't limited, so our number of sig figs should be 3. And lastly here we have another multiplication, so let's see how many we have. We have 1, 2, 3, 4 sig figs, and 1, 2, 3, 4, 5, 6 sig figs. So we should have 4 sig figs in our answer. That's Avogadro's number, and that's the Boltzmann constant, in case you're interested in. Of course, they don't have their units there, but, anyway. And again, when we write in scientific notation, the times 10 to the 23rd isn't part of the significant or non-significant. All right, for each of the following, identify what part of the scientific method it is. Possible choices are observation, experiment, hypothesis, law, or theory/model. And I know you guys had some pretty good discussion when you were working on this on Friday, and had some good little chats with me as well. So aluminum has a density of 2.70 grams per milliliter. Well, that's something that you could measure. And it's talking about just one element. So this is specific, and it's a measurement, so this is an observation. There we go. Next, chemical reactions are due to molecules colliding with proper orientation and sufficient energy. So saying due to is like saying because. It's giving a reason, an explanation. Explanations are either going to be hypotheses or theories. Hypotheses would be more specific, and theories would be more general. So referring to all chemical reactions, giving a reason, they happen because molecules collide with proper orientation, sufficient energy, that's a theory. In fact, we call this kinetic molecular theory of reactions, or kinetic molecular reaction theory. Next, the pressure of a gas is proportional to its temperature. Well, this is something you could measure. It's not saying why it's proportional, just that it is proportional. And it's a gas, not a specific gas, so any gas. This would be a law. Again, if it's something you see or measure and it's specific, it's an observation, generalizing those observations or applying those observations to many cases would be a law. Similarly, it's similar to hypothesis being the specific and theory being the more general. And lastly, I occasionally make mistakes in lecture because I haven't had enough coffee. Well, we've got a because statement in there, so that's an explanation, but it's pretty specific. It's just me making mistakes in lecture for that one reason. So this would be a hypothesis. All right. Now, last one here. For each of the following, identify what type of matter it is. Possible choices are heterogeneous mixture, homogeneous mixture, compound, or element. Gasoline. Now, you may be tempted to say compound, but the thing is gasoline is more than just octane. There are a bunch of other hydrocarbons in gasoline. So it's a mixture, and you can't separate them easily. It is a heterogeneous mixture. Damn it. Sorry, guys. It's a homogeneous mixture. I do apologize. I totally misspoke there. It's a homogeneous mixture because it is the same. Next, we have gold. Gold is an element. Now we have chicken noodle soup. Well, that's obviously a mixture, and in this case, it's a heterogeneous mixture. I was a little ahead of myself. And then lastly, we have sugar, which is a compound, sucrose. All right, so that does it for the Chapter 1 class activity. And if you have any additional questions, feel free to email me or stop by office hours. All right. In the meantime, stay safe out there. Bye now.